I'm Sean, I'm Sean Maxwell, and on behalf of the ARMA and the Technical Committee on Induced Seismicity, welcome everybody to our monthly webinars. Also part of the Technical Committee, Ahmad Ghassami, and then Jens Lundstern and Madi Haddad. So this week's webinar, if we just jump to the next slide, is going to be given by Jens. So we're appreciative to Jens for stepping up and providing the webinar this week. It's based on a publication that Jens is just coming out with, looking at mechanisms and stress inversions. So an interesting bit of material, and I'm sure it'll be of interest to the group here. So just before we pass it over to Jens, just want to quickly talk about the upcoming webinar schedule. So next month, February 2nd at the normal time, we have Bill Barnhart with the USGS. Bill is going to be presenting on INSAR and induced seismicity. Bill's been heavily engaged in a number of projects where INSAR is showing some interesting signals around induced seismicity case studies. So that'll be an interesting webinar. And then March 1st, we're going to have Hongfeng Yang. Hopefully I'm pronouncing the gentleman's names correctly, from the Chinese University of Hong Kong, giving a presentation on Sichuan Basin seismicity. And again, a topic that I think would be of interest to the community, and we're looking forward to that. The time is still to be determined on that, because since the gentleman's overseas giving the presentation, we might start at 9 instead of the normal 10, but keep tuned. We'll update everyone later on that. And then over to Madi.
Good morning, everyone. This is Mahdi Haddad from the Bureau of Economic Geology. Thank you so much for joining us for another great webinar that we are running this morning. First of all, please feel free to share the webinar invite to your colleagues who are interested in this topic. We have already almost 600 people in the distribution list, but we are looking forward to distributing this information to a larger community of induced seismicity. And please submit your questions during and after the talk in the chat function at the bottom of the Zoom meeting window, in order to use better of the webinar time. We ask everyone to send their questions to everyone, basically, in order for us to summarize the question. And basically, this meeting is being recorded, and the recording will be uploaded in our YouTube channel. And please subscribe to our YouTube channel in order to be notified for later recordings. Without further delay, let's invite Jens to take over the stage. Jens?
Thank you, Mati. I'm going to now share my slides. Sorry, it's going to take me a minute here, it looks like. And we're going to switch. And we're going to share. Okay, well, let me know if you have any trouble seeing anything or hearing me or whatever.
Looks good, Jens.
Okay, well, thank you both for, teeing this off. And it's fun to be on the other side of the webinar, like Sean was last month. So thank you all. And it's a pleasure to celebrate my birthday this way with all of you and talk about new research that I did with Eric Bosset at the Lamont Doherty Earth Observatory in Orlando, Tehran, who's now at ConocoPhillips. I'm going to be talking about focal mechanism stress inversions, so getting stress information from earthquake focal mechanisms, and specifically the little studied importance of having diverse nodal plane orientations, or diverse orientations of the causative faults. Let me do one thing here. Okay, well, the motivation for this talk is basically, or for this study really, is that there has been an increase in seismicity that most of you will be familiar with in the Permian Basin of West Texas and southeastern New Mexico that's shown on the map there. You can see the increase in this histogram here on the right. This has been updated through the end of last year now, and you can see that there was a marked increase in earthquakes, magnitude 3 and greater. And there's been a slight decrease last year. So some progress has been made in that front, but still a substantial increase from before. Earthquakes that have occurred since the TxNet array went online in 2017 are shown in red on this map. So you can see seismicity has migrated around the basin over time. These are thought to be, a lot of these earthquakes are thought to be triggered by oil, gas, and activities in one form or another. Whether that be wastewater disposal, hydraulic fracturing, EOR, and in some older cases, production. And it depends on the area. Now, these earthquakes, form lineaments like many earthquakes do in high quality seismic data sets like this double difference relocated catalog by Savitis and Lee for the Midland Odessa area here in the Midland Basin, sub-basin on the east side of the Permian Basin. And when you do double difference relocation, you can see that there's aligned groups of events. And this kind of raised a question of what happens if somebody were to do stress inversions on events from a very narrow range of fault orientations. And we were seeing that, I'm only showing 2 focal mechanisms here. These are older ones from the TxNet catalog. Depending on the catalog you use, there could be, there are quite a few more newer focal mechanisms. But you can imagine that we're looking at planes that are striking east-southeast for the most part, with a few that are east-northeast striking. So a very limited range of orientations. And in addition, it appears that these are very steeply dipping faults based on the limited information that's available. So probably around 80 degrees dip. So the question is, what happens if you do a stress inversion without a whole lot of diversity on those nodal planes? And this came up because when this is done, you sometimes see results that are a little different from the mapped stress orientations in the basin. And I'm going to be focusing on this area here that I just showed in the middle part of or the kind of western part of the Midland Basin here near Midland and Odessa. And stress inversions done on those kind of limited range of orientations of focal mechanisms tend to produce SH max orientation results that are different from what we mapped. This is mapping that I've been involved with over a few publications over the last few years for the Permian Basin. Most, though not all, of these measurements are from wellbore techniques, drilling-induced tensile fractures and borehole breakouts. Those are what's shown in black lines, interpolated across the basin in white there. And you see that on the east side of the basin, we have very consistent SH max orientations that are slightly close to east-west, maybe east-northeast, west-southwest, but not a lot of variability in that area. But as you move further west in the basin, we have these very interesting patterns across the Delaware subbasin here on the west side of this, really interesting 150-degree clockwise southward rotation of SH max orientations. And you can see that there's other variability that we don't have data for. Exactly, the existing data kind of hints at there being some substantial rotations that happen both to the north and south as well. So the stress field is well constrained, and we've also constrained the relative stress magnitudes in this area, dominantly using earthquake focal mechanisms. And so we're doing that using the AFI parameter, which is by Bob Simpson, which is a quantitative approach to determining illustrating the style of faulting or the relative magnitudes of the 3 principal stresses. It's a value that, for those not familiar, ranges from 0 as the most extensional case, 3 is the most compressive case. You can see the cooler colors are more extensional, and the Permian Basin is broadly extensional. The eastern parts, including most of the Midland Basin, we are somewhere close to AFI of 1.0, so between normal and strike slip faulting, both could be active in that area. And then further west in the Delaware side, we're still a little more compressive than pure normal faulting, so strike slip faulting will be active, but it is more extensional there. So that sort of sets up the question that we wanted to study, and I just want to emphasize the importance of understanding the stress field. I think for an ARMA audience, I probably don't need to say this, but I will anyway, that understanding stress is important for several reasons. including for production purposes. It helps you anticipate where a hydraulic fracture is going to propagate, how far it's going to go, and also for understanding induced seismicity in terms of determining which pre-existing fault orientations are most sensitive to failure in the stress field, or if you've already had an induced earthquake, how much pore pressure change might have been needed to trigger slip on that fault. I'm just demonstrating this for the Permian Basin. This is work that I did with Mark Zoback in 2018, where we took the new stress data for the basin. We broke it up into these study boxes of fairly consistent stress orientation and relative magnitude. And then using the fault slip potential tool by Stanford and ExxonMobil, we estimated the sensitivity of previously mapped faults across the basin in response to a small pore pressure increase, say due to wastewater disposal. And so the red faults are those that would be more sensitive, that would have a appreciable chance of becoming critically stressed in response to a modest pore pressure increase. And this is a fairly old fault data set. The Texas Bureau, led by Lily Horn and others, colleagues there, and the Scissor Group, have dramatically improved the fault mapping in various parts of the basin and have done fault slip potential studies across some parts. But this is just to illustrate, one of the main reasons to understand the stress field in detail, especially across an area like this, where there's a lot of variability in it. Okay, so what are we talking about today? I'm going to start by giving a few fundamentals of focal mechanisms in general and focal mechanism stress inversions. Some of you will know all of this already, but it's important to set up for a few reasons. Then I'll talk about the study methods. In brief, basically what we did was we conducted experiments on synthetic focal mechanism catalogs, but they were synthetic catalogs based on the observed earthquake lineaments, and the observed stress data, and I'll explain what that means. And so our goal is to try to replicate the mapped state of stress in stress inversion, see if we can get back the input stress values using varying amounts of diversity in the focal mechanism nodal plane orientations, or the causative fault orientations. The results, which may not come as a surprise since I am giving a talk on this, are that orientation diversity is indeed critical to obtain reliable stress inversions, and I will show what I mean by that in a few ways. But rather than just kind of leaving it there and kind of throwing a problem out to the community, we do introduce a few tools that might be useful, both for gauging the diversity of focal mechanism orientations and also for gauging the quality of your stress inversion. Okay, so to the fundamentals from the very beginning. What is an earthquake focal plane mechanism? Well, we're looking at an example here. This is a beach ball solution, as they're called. It's a lower hemisphere plot that provides a geometric description of the causative fault orientation for an earthquake and its slip direction. And it's usually determined by measuring seismic wave radiation patterns. And so this is a lower hemisphere plot. There's two planes visible in this plot. Here's one of them, and then here is the other one. So one of those two planes was the active fault. The other is what we call the auxiliary nodal plane. Without additional information, we don't know just from a single focal mechanism which of those was the real fault in the earth, but with additional information, we can constrain that. And so in this case, let's say the active fault was this red one here. So this is a shallowly east dipping fault. It's striking, so it's dipping off to the right or to the east in this plot. It's striking a little bit east of north. And so it corresponds to this block diagram example that we see on the right here, where there's north. Here's the fault plane. You can see that the strike is just a modest amount east of north. It is modestly dipping off to the east by some fairly small amount. And the slip angle is not purely strike slip. It's not exactly along the strike of that fault. It's some degree of reverse faulting motion. So this is an oblique reverse faulting earthquake closer to strike slip faulting. And that's what the focal mechanism shows. Okay, and I mentioned that the focal mechanisms also provide information and are determined usually by seismic wave radiation patterns. And so you'll see that they come with a p-axis or a compressive axis, where you can think of the material moving from here towards the fault, and a tensional axis, t-axis, where the material is moving away from the fault there. So as you can imagine, the focal mechanisms do provide us some information about the state of stress on the fault that produced the earthquake, because they include not only the orientation of that fault that failed, but also its slip vector. So they're really quite useful in that way, but they don't tell us everything about stress. So individual focal mechanisms by themselves are not sufficient for determining an SH max orientation. I'll get to that in a minute. But they do give you some general sense of what the maximum principal stress orientation was. It's probably somewhere within that P axis or that P quadrant there. And they provide constraints on the style of faulting. And you can see examples of different styles of faulting on the left here, where we have focal mechanisms ranging from normal faulting, oblique strike slip faulting, and so on, getting more compressive downward. And those are associated with different ranges of relative magnitudes of the three principal stresses, where extensional stress fields with normal faulting will have the vertical stress be the greatest principal stress. Strike slip faulting, the vertical stress will be somewhere in between the magnitudes of the two horizontal principal stresses, and reverse faulting, the vertical stress will be greater, will be the least principal stress. So they provide us some information about stress, but not everything, more constraints than anything. I'd like to make a quick aside here to talk about the stress mapping that we published in 2020 and updated in 2022 for North America, which is shown here. We're again using the AFI parameter to describe the style of faulting, and we're showing SH max orientations of these black bars, mostly from the world stress map, but also a few hundred new ones that were largely contributed by oil, gas, and geothermal companies. And the point of showing this is that we determined the style of faulting, or the colored background here, almost entirely from earthquake focal mechanisms. Where there were large numbers of focal mechanisms in an area, we did stress inversions on those, as I will be discussing here in a moment. But where in large parts of the continent, there are just sparse focal mechanisms available. And so we estimated the style of faulting on the AFI system based on those in a sort of interpretive approach. And so, there's areas that have, say, only normal faulting focal mechanisms, that you're somewhere within the normal faulting domain. Other areas that have both normal and strike slip faulting mechanisms, those are slightly more compressive, and so forth. So, this is just to highlight, kind of what focal mechanism data can provide you with. Again, this is the Permian Basin. The study area will be here in the Midland subbasin on the east side, where SH max is fairly close to east-west, east-northeast, west-southwest, and the style of faulting is normal and strike slip, slightly closer to normal. Now, I just mentioned that individual focal mechanisms do not provide reliable SH max orientations. And this is something that I just want to expand on slightly and show this figure from Dan McKenzie, who pointed this out back in 1969, where he's showing this is a lower hemisphere plot. It's not exactly a focal mechanism, but you can think of it, you can imagine where the focal mechanism would be here, because this is the P axis of that focal mechanism, and this is the tensional axis here with the T. And what he's saying is that for that given P axis, there is a wide range of different maximum principal stress, or S1 orientations, that could have caused that earthquake. And it varies as a function of the relative magnitudes of the three principal stresses, S1, S2, and S3. So as S1 gets much larger than the other two, you get better and better constraints on the orientation range for S1, up to this extreme case here. This is not using the AFI system, so it's a little unintuitive, but anyway, up to the extreme case where there's a limited range of orientations that S1 can have. But in almost all cases, you're dealing with a wide range of possible principal stress orientations associated with a single focal mechanism. And of course, we don't necessarily know the relative stress magnitudes in advance. This is where stress inversions come in. And the idea behind the stress inversion is that you have a large group, let's say twice this many, maybe 30 well-constrained earthquake focal mechanisms that occurred in a localized area where you think the state of stress is broadly uniform. Doesn't have to be exactly uniform, but it has to be close enough. And then you're applying a mathematical approach to determine the stress tensor. It's not the absolute stress tensor, it's the relative dimensionless stress tensor. But this is a quite powerful approach, because without spending any money, such as drilling a well or something like that, you can determine the orientations not just of one of the principal stresses, but of all three of them, and the relative magnitudes of them, just using existing focal mechanism catalogs. So it's quite powerful and an accessible tool and widely used because of that. I very much avoid putting math in my slides in general, but I'm going to do that here against my better judgment because I think it's pretty important for what we're about to talk about, and it would be kind of almost offensive to not describe this mathematical process in terms of the math behind it. And it's also important for the tools that I'll be describing towards the end. So a focal mechanism stress inversion is trying to determine stress tensor components. These are in this vector M here. So the stress tensor components of interest, M, using information from focal mechanisms. So in this case, the slip vectors, which are in this vector, or the slip vectors, which are in this vector here. You have to relate those two things together. So there's a forward operator, G, and that's what's shown, a subset of that here. And the idea is that we're making an assumption that, and it's a fundamental assumption to all stress inversions, that the orientation of maximum shear stress on a given fault plane that produce an earthquake, that will be exactly the same as the orientation that fault slipped. So, it's a fairly straightforward assumption. The fault will slip in the direction of maximum shear stress applied on it. It's called the Wallace-Bach criterion. And that allows us to build this this matrix relating fault orientations and to stress. Okay, but we're doing an inversion, so we're finding m hat, or the stress values, and from the slip vectors S, and so we need a different matrix, an inverse operator L. That inverse operator L is fairly straightforward using Tarantola and Vallet's solution. It's just taking the forward operator that I already mentioned, G, and a data covariance matrix, C sub D. And so I won't go into this any more than that, but I'm highlighting this data covariance matrix because it'll be helpful for us later in terms of tools for determining the reliability of stress inversions. Okay. Stress inversions make some very important assumptions, and that's sort of the root of the discussion of the presentation today. And in the new paper that we just published a few days ago in the Geological Society London special publication, we point out the 5 that we think are sort of the main assumptions of stress inversions, and there could be others that we're not thinking of. The first one I've already mentioned, and that is that the slip vectors on focal mechanisms, so the direction the fault slips, is the same as the maximum resolved shear stress on that fault. Again, the Wallace-Bach criterion. Second is that the active fault plane can be identified from the 2 nodal planes. I mentioned that without additional information, we don't know which of those 2 was the real fault. But stress inversion methods, such as a recent one by Eric Bosset, published a couple years ago, are getting better and better at using an iterative process, taking advantage of all the information provided by a whole suite of focal mechanisms to identify which faults are the active planes for each focal mechanism. Third assumption is fairly straightforward and obvious one. The focal mechanisms that you use for the inversion have to be reliable. I hope that the screen has come back for you all because it just disappeared for me. But the focal mechanisms must be reliable. It's a straightforward comment, but it's quite important considering that focal mechanisms are usually determined by seismic wave radiation patterns, so they require good azimuthal coverage on seismometers and things like a reliable velocity model and good depth information to provide good constraints on the geometries. I also mentioned this already. You need approximately the same stress field for all mechanisms that you use. Those earthquakes have to occur in approximately the same stress field, and that's the stress field you're trying to determine from the inversion. It doesn't have to be exactly the same. Andy Michael has shown this in the past, but that is an important one. And finally, what we'll be focusing on today is that fault plane orientations need to be diverse. And this one is very rarely considered and has been studied in only 2 cases that I can think of, one by Gene Hardebeck at the USGS and one by John Townend at the University of Victoria, Wellington. This relates very directly to what I mentioned, Dan McKenzie's argument that a single focal mechanism is not sufficient. for determining reliable orientations of principal stresses or relative magnitudes for that matter. So you can imagine in the most extreme case, which we will study here, of identical focal mechanisms all drawn from the same fault that someone's trying to do a stress inversion on, that's essentially the same thing as doing a stress inversion on a single focal mechanism. It doesn't provide much leverage for that inversion. And so related to that, you need a sufficient number of mechanisms, ideally something like 30 or more. Okay, so that's the background. Let's talk about what we did. As I mentioned, these are synthetic experiments on data-informed catalogs of focal mechanisms, and we're trying to get back the input stress value and seeing how well we do as a function of the diversity of the fault plane orientations. And so I mentioned the study area here. It's in the Midland Basin on the eastern side of the Permian Basin, where we have the high quality relocated earthquake catalogs show these aligned groups of events. We have fit planes to those. So the orientations of these aligned events, these lineaments, we're assuming are the strike of a focal mechanism. The dip is a little less well constrained, but it appears from a few different sources of information that they're dipping around 80 degrees. They're fairly steeply dipping faults in this area for the most part. And the other component you need to create a stress inversion is, a synthetic stress inversion is the slip vector. And we are applying a slip vector based on the mapped stresses across this area, which, as I've already said, this is an interpolated SH max orientation that's it's close to east-northeast, west-southwest. And the relative stress magnitudes are just a little less than 1, so strike slip normal faulting. Okay, so this allows us to create synthetic focal mechanisms in dark gray for each of these aligned groups of real earthquakes that are defining something like the fault that failed. And what we want to do is see what happens if someone were to do a stress inversion on a limited range of orientations here using these synthetic mechanisms. Are they able to get back the observed stress values? So these are not very diverse plane orientations. There's several ways to show that. Here's one in this lower hemisphere plot on the right here. Most of the planes strike about east-southeast. They're dipping steeply to the south. We allowed one to dip steeply to the north to increase the orientation diversity for that. And then there's 2 planes that strike east-northeast. And so you can just see the clustering there. This is a Moore circle showing the state of stress, the kind of average state of stress in this area. It does vary slightly across the area, but not very much. So this is sort of the average state of stress. And these are the lineament orientations. So the strikes and dips of those planes. This is the shear stress versus normal stress resolved on those planes within that stress field. And you see that they are close to the failure line, not exactly touching that failure line. But these are generally well-oriented faults that probably experienced a little bit of pore pressure increase before they failed, which is consistent with the thinking that these are probably triggered in many cases by wastewater disposal in this area. Okay, and what we did next was we populated these catalogs based on the initial synthetic focal mechanisms. So nothing sophisticated here. We basically just copied and pasted 29 times to create 30 of identical focal mechanisms for each lineament. And so you can imagine doing a stress inversion on just these 30 focal mechanisms that are identical associated with this one lineament. And that's sort of the worst case of least diversity that we will study. But we also applied noise. So we created additional focal mechanism catalogs where we applied varying amounts of noise to those to simulate real situations where in real life we tend to see some variability in the orientations that is entirely a result of uncertainty in the measurements for that focal mechanism. And so just for 2 of the lineaments here, number 2 and number 10, so there's number 2 on the map and there's number 10 on the map, the actual lineament orientation that we used, shown in black, dipping steeply to the south. And then the red lines are 5 degrees of noise added to that plane. So that's 30 focal mechanisms with 5 degrees of noise. Gold planes are 15 degrees of noise added. And then we did a 30 degrees, a very high noise kind of catalog that's in blue. And then we tested those. So let's get to the results then. Having set that up, as I mentioned, orientation diversity is critical for reliable inversions. That's what we found. You can see that just from this first slide. where we did sort of the worst possible case, where we just said, what if someone took a stress inversion of 30 focal mechanisms that all came from the same fault? And we did that for each of the 10 lineaments, just to really drive this home. And so what's shown here on the in these plots, the upper ones are the SH max orientation returned from the inversions, maximum horizontal principal stress, and the lower ones are the AFE value, or the relative stress magnitudes determined from the inversions for each of the 10 lineaments. The colors in the dots represent how much noise was added to the catalog. So the solid, the darkest dots are the highest quality, no uncertainty, no noise added. These are identical focal mechanisms. They're all being inverted for that fault, if that makes sense. So there's no uncertainty bars on those, but the others have uncertainties determined from bootstrapping. And so what you see here is kind of bleak, really. It's that in no cases do we get, do the stress inversion results match the input SH max or AFE values. So the input values are shown in black here, and we would hope that some of these dots would touch the black lines or the black dots, or at least that their uncertainty ranges would include them. But worryingly, even the uncertainty ranges in 0 cases from bootstrapping, this is, I believe this is a 1 sigma uncertainty range. In none of those cases does that uncertainty range even include the input stress values. So that's really quite problematic. And what it indicates is that when doing a bootstrapping in a case like this, where we violated one of the assumptions of the stress inversion, that orientations of the nodal planes need to be diverse, bootstrapping can underestimate the uncertainties and lead one to think that their results are much better than they actually are. Okay, but as I mentioned, this is sort of a worst case where someone is taking focal mechanisms all from the same fault and trying to do a stress inversion on that. What if you did a little better? We'll look at this red group here where someone, where we've taken east-southeast striking lineaments only. So it's a very low focal mechanism plane diversity, but it's a little better than just from a single mechanism. And we can just look at the red example, which is a little better. It's 35 focal mechanisms. That's a good, a good number. And these plots are similar. We're showing the SH max orientation on top and the relative stress magnitudes at the bottom, determined from the inversion as a function of the amount of noise added to the catalog. So the 0 degree noise is on the left here. That would be a case, kind of the ideal perfect case of no noise. These are fully reliable focal mechanisms, unlike what we work with in real life. And you see that in these low diversity cases, unsurprisingly, it does a very bad job of matching the input SH max orientations and AFE values, which are the black lines, black horizontal lines. I mentioned that there's a slight variability in stress values across the study area. So that's the gray zone around these. So it's a variability in SH max orientation, and AFE is very hard to see, but it's only very slightly. But in these low diversity cases, uncertainties are, again, dramatically underestimated. And so bootstrapping, again, makes it seem like the results are better than they actually are. And one would have no idea how wrong their stress inversions were just looking at this. We try a marginal quality case where, let's just look at the darker blue ones, where we take 35 focal mechanisms, so a decent number, from all of the lineaments. It's not a wide range of lineament orientations, but now we are working with both the east-southeast and east-northeast striking ones. So there's a little bit of leverage there for the inversion. And you can see for the blue there that they actually, when we have very well-constrained focal mechanisms, we actually do decently well, and we are able to replicate the input stress values or close to. So, that's a little less troubling, but as soon as the noise starts to creep up towards values that we might have in real life, then we end up with the same problem where we've done a bad job of matching the input stresses. And then the final case, this is the one case, so let's just look at group 6. This is a larger number of focal mechanisms, 50, so it's a really good number. And in this case, rather than basing the focal mechanism orientations off of the observed fault orientations in the basin, we said, let's find near optimal oriented faults, but a broad range. So they're not perfectly oriented, but they're near perfectly oriented faults in a range of orientations, and do stress inversions on that, so the dark green. And that, you can see, does much better, even as noise increases substantially. So noise doesn't even matter all that much when you have a really diverse range of focal mechanism orientations, which of course in nature you may not have. But this is to emphasize, the difference between low quality, marginal, and high quality when it comes to diversity of focal mechanisms. Okay, this is showing the results a different way, where we're looking at the low diversity case on top here, and of just the east-southeast striking planes, and we're looking at the high diversity case on the bottom here, where we're taking optimally oriented planes that are not based on the limited range of real faults in the Permian Basin. And these are lower hemisphere plots showing the three principal stresses determined from the inversion. The inputs were vertical and horizontal, and we would hope that the SH max orientation, that one of the principal stresses, S2 in particular, should touch or should be very close to the SH max orientation, which it is not for the low quality case, but it is for the high quality case. But I'm showing this because there's, interestingly, the 95% confidence intervals, again determined by bootstrapping here, are shown. And very interestingly, in none of the cases from the low quality inversion do the deterministic results from the stress inversion in terms of orientations of the three principal stresses, in no cases do they fall within their own 95-degree confidence values. So that's kind of a troubling and interesting scenario here. And I think what's happening is that this is a function of bootstrapping being done for a very narrow range of fault, or just a couple of fault orientations, east, southeast, and east, northeast striking planes. And in many of the bootstrapping iterations, sampling will miss the few northeast, northeast striking lineaments. And so a large number of the bootstrap samples will suggest a different stress field. And enough of those occur that the 95% confidence interval doesn't even include the deterministic value. Now, for group 6, the higher quality values, the 95% confidence intervals, although large, are falling around the deterministic values from the inversion, and the deterministic values from the inversion do a good job of replicating the inputs. But I do want to emphasize this, that even in a near optimal case of high focal mechanism orientation diversity, we have some pretty broad 95-degree confidence intervals that form this girdle here between the SH max, the SV or S1, maximum principal stress direction here, that's vertical, and S2, the maximum horizontal principal stress direction. And so why that is, I think, is that in this case, I mentioned, AFI is close to 1, so the vertical and maximum horizontal principal stresses are similar in magnitude. And so bootstrapping in some cases, depending on which subset of focal mechanisms are included in a bootstrap sample, are likely to find, in some cases that the S1 is horizontal, and in some cases that it's vertical. And so it'll flip them around in some cases and form this girdle here. And this is a function of the specific study design in this case, in that we have AFI values close to 1. But I think it's a good cautionary example that the relative stress magnitudes matter in terms of how reliable the inversion is. In other words, you might need to have an even better constrained inversion in certain cases, such as where the two of the three principal stresses are similar in their magnitudes. So the inversion will have less leverage in that case. This is another slide showing kind of what we think is going on here. And this is another Moore circle. And what this is to show is if you were to do one of these really low quality stress inversions just on the lowest diversity case, where you're doing stress inversion on focal mechanisms, all from the same fault of the same orientation. We've added 5 degrees of noise here. This is the stress field that you get. And if you remember earlier, there's the Moore circle was quite different. The vertical stress in reality in this study area, vertical stress is the greatest, and the maximum horizontal stress is only slightly less. So this is quite a different stress field that it's determined. And if you were to plot the orientations of those planes used to determine the stress field in that stress field, so if you were to determine the shear and normal stress on those planes, it very interestingly is maximizing the shear stress on those planes. So you'll note that they have very high shear stress values. They're kind of at the top of the Moore circle, and they're not near the failure line, even though In this case, we know these faults fail. It's reasonable to assume they're near the failure line, and within the observed stress field, I'd already shown that they are pretty close to the failure line. So that appears to be what's happening. The inversion is maximizing shear stress where it lacks enough information from diverse plane orientations. This is to show a slightly better case. So if you were to do a marginal quality inversion from both the east-southeast and east-northeast striking planes, you get a Moore circle that is not quite right, but is closer to the input values. So that's what this is, the stress values here. And if you were to map those same planes, determine the relative stress magnitudes on those same planes, or I'm sorry, the shear stress versus normal stress on those lineament 2 planes, in this case, they do a much better job of getting close to the failure line. So this is to show that where more information is available, the stress inversion is reverting less to assuming that, maximizing the shear stress on the planes. And this is to show the same thing just for a different lineament, and it just shows again for lineament 10 that if you have a limited case, limited orientation diversity, that the plane it'll maximize shear stress on those planes. But if for the same planes, but you're doing a stress inversion on a broader range of plane orientations, better stress inversion, they end up being closer to the failure line. Okay, so results. I'd like to talk about some tools that we have introduced, as well as other ones that we highlight that are already in existence for gauging orientation diversity and inversion quality, reliability, because I've sort of created a problem here that people need to worry about in terms of their focal mechanism stress inversions. And I don't just want to leave it there and kind of say, good luck. I want to show some ways that one can determine whether their stress inversions are reliable given these factors. But first, a logical question from this study, and one that the reviewers asked, is, well, how much orientation diversity actually is enough? Can you provide quantitative values? And the answer is very unsatisfying. It's that it really depends. It depends on a lot of factors. Depends on the stress inversion method. We are using high quality modern stress inversion methods by Vrvruchek and by Eric Bosset that do a pretty good job of identifying the true planes in most cases of the 2 nodal planes. But with older stress inversion techniques, you may require more orientation diversity. And as stress inversion methods continue to improve over the years, there may be less need for as much orientation diversity. As I showed, it depends on relative stress magnitudes. So if 2 of the 3 principal stresses are similar in their magnitude, you might need more orientation diversity. Same is true if the pore pressure is high. You may end up needing more orientation diversity because the 3 principal stresses are more similar in magnitude. As focal mechanism reliability deteriorates, you need more stress inversion, you need more diversity in orientations as well. Same thing if you have few mechanisms. And if there are localized changes in the stress field, this throws off stress inversions to some degree, varying by how much variability in the stress field. And so you'll want, you might need more diversity in those nodal plane orientations to get a reliable inversion. Okay, so how do you determine the orientation diversity of your set of data that you're using to do a stress inversion? There are several ways this can be done, kind of qualitatively and quantitatively. And this is a visual qualitative approach, shown two visual approaches here. In this case, for the examples in this study, these are the compressional axes, the p-axes, for these 10 synthetic focal mechanisms for each of these faults that produce the earthquakes in the Midland Basin. And you can see we have trouble. We have problems. There's clustering in those orientations. But there is a little bit of value. There's a little bit of variability, but there's a lot of clustering. And these are the east-southeast striking planes that really give you very limited range of orientation diversity. This is another way of plotting orientations. It's the focal mechanism B-axis plunge versus plunge of the T-axis versus the plunge of the P-axis. I didn't mention the B-axis, but that's the neutral axis of the focal mechanism. And in this case, you can see these are the same focal mechanisms. You can see that there is a little bit of diversity here, but they are kind of in this very interesting pattern of being strung out in this line that that suggests to me that there may be a little bit too much structure in this data to provide a reliable stress inversion. That's all qualitative. We can think about quantitative approaches as well, and we don't establish an absolute value that studies should all meet. But for our particular study, these are quantifications of the diversity of the focal mechanism orientations, and what we prefer is to find the average focal mechanism. So in this case, it was the element-wise average from the moment tensor underlying the focal mechanism. So this is, let's say, the average focal mechanism. And then we find the median difference in orientation between all of those focal mechanisms used and the average one. So it's the median Kagan angle to the average focal mechanism. In low-quality inversion cases of just the east-southeast striking planes, we have a very limited median Kagan angle, 6.5 degrees. In the marginal case, it's not much higher. It's only 7.3 degrees. And in the very high quality case, it's very high. It's 43 degrees. So I realized that there's a lot of difference between high quality and marginal, and not a lot of difference between marginal and low quality. So it's a little hard to determine a threshold here. But in our particular case, I would think maybe something around 10 degrees might be a threshold that would be useful for differentiating between a marginal and a higher quality case. Now, luckily, we don't have to, wave arms quite that much in practice. We there are some tools at our disposal that we can use for determining the actual quality of the focal mechanism stress inversion, and really the how unique the results are. And that gets us back to this earlier slide that I showed, that sort of the definition of stress inversion mathematically, when I showed that we're trying to determine M, the stress tensor components, from S, the shear traction orientations. These are from the focal mechanisms. And we need an inverse operator L. This is how I define the inverse operator here. This is actually how Tarantola and Vallette defined it. And it uses this forward operator relating shear stress directions, slip vector directions to shear stresses using the Wallace-Bach criterion. And it also uses a data covariance matrix. Okay, so it's fairly straightforward. I show this just because the tool that we emphasize that is very useful for determining the quality of a stress inversion is the posterior covariance operator. This matrix C hat M. And it's actually fairly simple to format. It's just this forward operator, G, and the data covariance matrix, C sub D. So I won't get into any more math than that, but just this is laid out in the paper, how this is done. But I want to show what it actually looks like, what this matrix looks like. So if you color code the values on that, this is the posterior covariance operator, C sub M, C hat sub M. And what it includes in this case is the inverted stress tensor parameters versus the true stress tensor parameters. And it's a posterior covariance between those. So we would hope that the on-diagonal components have higher covariance than the off-diagonal components. We don't want there to be much covariance between different stress tensor components because that suggests that the stress inversion is less unique. And so this is the high diversity case where we really had near optimal data, synthetic data. And you can see that we have strong on-diagonal components for this, and only only kind of modestly large, in this case, negative covariance on one of the off-diagonal components relating sigma 2,2 to sigma 1,1 in this case. So this is for our data set. Now you can also normalize the posterior covariance operator to provide a little more information about the quality of the inversion, and that's what's shown on the right here. So we've normalized everything so that the on-diagonal components are 1. Everything is relative to these on-diagonal components. And so this allows you to see, whether any of the off-diagonal components are especially high relative to one another. And, what we see here is that there's just kind of modest covariance on the off-diagonal components, indicating a pretty reliable, unique stress inversion. And You can tell the difference by comparing to lower quality cases. This is the marginal quality case here, where we are drawing focal mechanisms from planes striking only east-northeast and east-southeast. And this is the low quality case, where we are limited to only the east-southeast striking fault, so a really bad case. And you can see the deterioration of these quality indicators as you go down and get lower quality stress inversions, where for the marginal case, we now only have 2 or maybe 3 on-diagonal components that are especially strong relative to the others, and we have quite a few off-diagonal components that have larger covariance. And you can see again, note also the change in scale for the color bar. The covariance values are increasing as you get worse stress inversion results. So this gives you a way to quantify the covariance in your stress tensor components determined from the inversion. And then the worst case down here, you see that there's only one on-diagonal component that has a higher covariance relative to the off-diagonal component. So that means that the inverted model parameters are really covarying strongly between one another, and so it's hard. Your stress inversion has less reliability and uniqueness to its values, and you can see that again if you normalize the posterior covariance operator to the on diagonals here. That relative to sigma 1,1, all 4 of the other stress tensor components have high covariance, so not doing a good job with those. I'll leave it at that and just say that we have created tools to apply these methods so people can actually test out the posterior covariance, normalized posterior covariance, and other things I have not described because they get a little more mathematical. But this is available on Eric Bosset's GitHub page, so you can just put in your focal mechanism data set and estimate the quality of your inversion there. So didn't want to just leave people with that, and I'll conclude now and say focal mechanism stress inversions, as I've shown, rely on several key assumptions, including, importantly, that nodal plane orientation diversity is adequate. If one of those is not met, the results can be unreliable, that problems can be compounded if additional assumptions of these inversion methods are violated, like you don't have enough mechanisms and you don't have enough diversity in them. Worryingly, bootstrapping can underestimate the uncertainties, but luckily there are other tools available to use in concert with bootstrapping. I don't want to say bootstrapping should be discarded because it's very valuable, but other tools such as the posterior covariance matrix can help gauge the inversion quality. And I'll just end on a more optimistic note. I think you can interpret what I've described so far as fairly pessimistic, and I want to point out that stress inversions are very reliable if the assumptions are met. This is our stress mapping from the Permian Basin. Almost all of these stress measurements, the unadorned lines, are from wellbore measurements, but you can see a handful of them are from focal mechanism stress inversions. And this was before I was even thinking about this issue, that the focal mechanism derived SH max orientations agree quite well with the wellbore derived ones across the basin, even as the stresses change. So it's just to emphasize, I do not want to discourage anyone from this very accessible, useful technique, but you have to be mindful of the assumptions. Thank you.
Great. Well, thanks for that, Jens. Thanks for the excellent presentation. And I was kind of giggling to myself when you were talking about optimism versus pessimism in this, but it's probably realism that we need, right? Of knowing the limits of the assumption and the impact on the results. I like the way you wrapped it up with the work back to the stress map, and there's a few questions, but before we get to it, I was gonna maybe just ask that, based on what you know now, would you change some of the criteria for the input parameter that was used for the stress map, or did you already have an intuitive feel for this kind of QC aspect?
Yeah, I think based on this, I would hope that quality criteria for stress inversion results can incorporate something about the nodal plane diversity. I don't want to be too prescriptive about that because, as I mentioned, as stress inversion methods get better, you might need less orientation diversity. And in some cases, certain relative stress magnitudes, it just doesn't matter as much. But it would be great if people reported some of these values when they do stress inversions. And, so I would certainly, for any updates to the stress mapping, I will be paying a lot more attention and running these tools to see what the variability in nodal plane orientations actually is, and using that to screen out, inversion results as needed.
Great. And so a couple questions from the participants. One, Thomas Joe is asking a question. So you referred to a friction coefficient of 0.7. He's wondering how you got that value, and maybe just to generalize a bit, is there anything specific that presumably the results are kind of independent of that specific value? But
yeah, right. So the friction coefficient value, that's based on, that's just sort of a guess at the friction value. Based on Byerly's law, it'll be somewhere between 0.6 and 0.85 or something like that. You could use 0.6 instead of that equally. So, the results are largely independent of that. The plots will look a little different, but it doesn't actually, hinge upon the choice of friction value. But I'll just say that something like 0.6 or 0.7 is pretty reasonable for most of these cases.
great. And then question from Adam Begg. He's wondering about kind of the condition number from an inversion, and whether or not that's a good proxy for the diversity.
Yeah, this is a little bit past my wheelhouse, Adam. I think this is a great question, whether you can, I'll just try to distill it and say, rather than doing the posterior covariance operator or visualizing the orientation diversity for nodal planes, what if you looked at the condition number of the forward operator, the G matrix? And I might actually punt on this one because I'm not sure I could give a, so this is the, actually move way, apologies for the fast forward, but fast backward. I'll punt on this one a little bit and just say that I refer for questions on this one, I think, to Eric Bosset, who could say this. Actually, these figures just came straight out of one of his papers for stress inversions. But my sense is that you might be able to do that.
Great. And then Ryan Schultz is asking, if there's any thoughts you have on inversions that might be more robust to deal with kind of this, either view it as a sparse sampling or consistent mechanism problem, the diversity problem, I guess.
Yeah, what sort of algorithm? So how would you improve stress inversion methods?
Yeah. And maybe
yeah,
just
that's a
maybe just to generalize it a little bit, Jens, I know, is there additional information that could be brought in for constraints to help in cases where there isn't great diversity, to help stabilize the inversion?
We have been thinking about this, and I will say one thing. I did not get into this at all for simplicity here, but Eric Bosset, actually this paper right here, Eric introduced an improved stress inversion method that gets around the common assumption that the shear tractions, S here, that they are all equal. So most stress inversions are linearized by assuming that these are equal. It's an assumption that's made. And it's a fairly reasonable assumption because, if these fall, at least in a not induced seismicity context, in natural seismicity, you expect the faults that failed to be quite well oriented within the stress field. Eric's inversion does an additional iteration that allows you to allows it to vary that. And our paper shows the results for both methods, with a fixed shear stress and variable shear stress. And actually, sometimes the variable shear stress method does do better. And so that actually is a direct answer to your question, Ryan. But we point out ways it doesn't always do better. It gets a little complicated, but my thinking is that in induced seismicity cases, particularly cases with very high pore pressures where there's a wide range of faults that are active, not just the two best oriented ones, that allowing the shear stress magnitude to change is good, because probably the shear stress magnitude on those faults really did change. But then there are cases, certain relative stress magnitudes and so on, where it's actually better to have the fixed shear stress values, like is traditionally done, like in the Vervuchik and Andy Michael methods. So it's a little bit complicated. I refer you to the paper, but I think absolutely. We have thought about this a little more. I have wondered, I don't know whether this is possible, whether you can constrain the shear stress magnitudes on those faults based on some other information, like assuming the crust is critically stressed. And so, you have some idea of the magnitudes of those. It would probably have to be iterative, or maybe with a stress drop from the earthquakes, although those are highly uncertain usually. So see Sean rolling eyes possibly. So, anyway, there may be approaches. Yeah, good question, Ryan.
Yeah, sorry, I don't think I was rolling my eyes, just
Oh, okay. I was rolling my eyes internally a little bit because I know it's a challenge. So
yeah, it is. But we reached the end of the hour, so on behalf of ARMA and the technical committee, I'd like to thank Jens for the presentation and thank everybody for the interest and the attendance today. Just a reminder to everyone, the next webinar, February 2nd, Bill Barnhart with USGS will be presenting on INSAR. So I'm sure it'll be some really interesting case studies. Look forward to that. So watch here for the invitation from Madi for that one, and hope to see everyone next month. And again, thank you, Jens.
thanks, everybody. Happy to answer any questions for anybody informally.
Yeah, so I think there was one other one came in from Mariana Rodriguez. Mariana, if you're there, do you want to unmute and ask your question?
Yeah, or I can send it an email. I mean, or what? I mean, I don't want to take more of your time. Whatever you prefer.
I've got time.
Okay, yeah, it's a very basic question. I'm very new in this field, but a very great talk, so it was very informative for me. Just a very basic question. So when you do all the inversion and you get all the stresses, do you do any kind of analysis or update in the calculations, or to make sure you find a smooth and continuous stress field?
I don't do that. There are stress inversion methods that are damped, spatially damped. I think Gene Hardebeck, and I forget who else, has been involved in creating those. So there are ways to take advantage of the regional consistency of, or coherency of stress field over space to make the inversion results a little more stable. We were not doing anything that accounts for that at all. We were using the more traditional approaches, although they're newer. These are not old methods we're using, but we are not using spatial damping. So yeah, that could be done. In the mapping, the stress maps, we have interpolated the relative stress magnitudes, the colored background of those maps. So there is some smoothing that happens there.
Okay, thank you.
Great. Well, Jens, I'm gonna have to run myself, but yeah, thanks for this. And thanks, everyone. We'll see you in less than a month.
Less than a month.
3
I'll
weeks.
stay on for just a minute in case there are more questions, but see you, Sean.
See you later, guys.
Jens, thank you so much. It was a great webinar. Good job.
Good. Thank you.
I need to follow up with the papers, actually, the formulation, and it was very interesting to me. I was looking for this sort of explanation of the focal mechanism inversion. So I will definitely need to read the papers, and we can talk about it later, maybe.
Yeah, happy to. It was a fun study to be part of, and great co-authors. So yeah,
Definitely.
absolutely.
Yeah, exactly.
Well, I guess unless
So
there are any other questions.
I have one question. So how about the classification of these focal mechanisms versus depth and find how much the stress can change in depth. Do you think it can be a big variation of that if you go from the sedimentary rock versus the crystalline basement?
Now, that's a question
Maybe.
that comes up a lot. We don't see evidence of that in the places we've worked, except in a couple. It may happen in Western Canada sedimentary basin between the sediments and the crystalline rocks beneath them. It may happen in, I'm familiar with a case in Colombia where it may happen as well. But for the most part, we don't see changes with depth in orientation or relative magnitude. And, you know, there's some noise in the orientations and probably in the relative magnitude too. And I'll give one caveat, and that is that in, you know, within sedimentary successions, if you have viscous stress relaxation happening in a clay-rich rock, there can be changes in the relative stress magnitude, and that's kind of a challenge for efforts to determine the values of SH-min as clay content goes up, because the three principal stresses might not have the same ratio, but that's like one case. But yeah, but generally speaking, no.
Yeah, and I had another question. So how about the if you consider the disturbance of the stress because of the sequential reactivation of faults, if you consider some disturbance of this stress, then we are not dealing with the same stress matrix for each of these fault reactivation. So
yeah, that's a great question, and I think it's one that is really not well understood. You know, it gets to the question of whether you can use aftershocks in a stress inversion, and some people have written about that. I think Patricia Martinez Garzón has argued that it's better to use declustered focal mechanism catalogs, because then you're dealing with less risk of your focal mechanisms being what you said, you know, that one earthquake is occurring in a stress field that's been perturbed by the prior earthquake. I don't think there's been a lot of work on that though, and so yeah, there is something to study for sure.
Yeah, great. Thank you so much again. It was great, very thought-provoking actually.
What's that?
And it was very thought-provoking.
Good.
And the other thing is, a lot of people asked me about the recording. So this is being recorded, and it will be uploaded on our YouTube channel for them to review. So,
thank you for doing that.
Yeah, sure.
All right, see everybody later.
Yeah, see you later. Have a good weekend.